All right. So, uh, this is the first uh, study stream for uh, this new book that we're doing with Software Over Coffee. It's called Designing Data Intensive Applications. My name is Michael Kaufman. I help run the club, and if you are interested in joining our community, um, yeah, leave a reply and definitely shoot you an invite to our Discord. Um, we meet every Sunday at 7:30 p.m. Eastern time, but discussions can take place at any time. So, um, yeah, this book is phenomenal. I'm extremely excited to get into it. I've read ahead a few of the chapters, and I'm going to be going through and doing a proper, thorough outline and rereading a lot of the content. Um, I don't think I've really. I, some of my goals in doing the chapter summaries and chapter reviews is twofold. And we talked a little bit about this as a group last time. And this is the idea that, back when we were in school, we would take notes to pass the grade, right? We would take notes to pass the test. I'd be able to take um, notes and then pass those notes to you, and they would be useful, right? Because I would focus on um, if I was a good note taker, right? If I was a 4.0 A plus student, I might know what to look for, right? And so as a result, I might pass those notes to you, and then you would say, got it. These are the things to focus on, right? These are the cliff notes. As you progress through your professional career, I think that changes somewhat, and the notes become much more subjective, right? Like, I don't know where your baseline and what your background really is, and then over time that our experiences diverge. There's some obvious differences, right? You might be a front end engineer as opposed to a back end engineer. You might have spent a lot of time writing systems level code. You might be a C++ programmer, where somebody else might be doing functional closure work. Who knows, right? And so that, with all these different backgrounds that we have within software, it's sometimes challenging to create notes that are useful for everybody. Nevertheless, I think that there are certain key takeaways that every um, book has. Things that the author is trying to convey, some key takeaways. And so one of my goals as I read books, this book is one example. I think a better book would be a lot of the Martin Fowler books, or the book that we're reading at work, Implementing Domain-Driven Design. When you read those books, um, I often find myself disagreeing with the author or having a different opinion, right? Clean Code is another example of a book where, um, folks who have had a bit more experience within the field may disagree with certain aspects of the book. But I think it's still important to try to understand what the author was trying to say, and then um, express your notes in that way. So that is one facet, right? That is one facet of what I would like to do with some of my note taking, is take notes from the author's perspective. Like, do I understand what Martin Kleppman is trying to teach me? The other type of note that I think I'd like to, we talked about this in our group, is what are those aha moments that make me go and say, oh, remember that bit. Um, that might be useful or applicable to where I currently am, right? So I think as I take these notes, I will try to make a distinction, what is a personal aha moment versus and things that are relevant for me or things that I think might be interesting to discuss with the group, um, and notes that are somewhat objective. All right, so laying out the groundwork. Take a sip of my coffee, my decaf coffee. It is late, so I have no idea how far I'm going to get in this. To be perfectly frank, this could be a 10-minute stream, but um, yeah, I don't know what I'm going to do with this video. Might share it on YouTube, get that going. This is a first, um, but if questions come in through Twitch, whatever, be happy to interact. See where this goes. All right. So, designing data-intensive applications. The big ideas behind reliable, scalable, and maintainable systems. So I think right out of the gate, right, I think there's a lot that you can infer from the title, and I don't think that, at least having, again, looked ahead through some of the chapters, these are some of the key themes here. The notion of what is a reliable system, what is a scalable system, and what are some of the best practices to maintain it. So I'm going to write that down. Key themes. Reliable, scalable, maintainable. All right. All right. Let's open it up. Now, the way I've got the video set up here, I think I'm going to have to move the book around a little bit as I go page to page. So do bear with me. I'll hopefully try to get used to it. But, in fact, let me put this little marker here to off surface. That'll do, right? So that's going to be my indicator for where I should move the page to and from. So let's go ahead and read the forward here. So we're not sure what the section's called, but technology is a powerful force in our society. Data, software, and communication can be used for bad, to entrench unfair power structures, to undermine human rights, and to protect vested interests. But they can also be used for good, to make underrepresented people's voices heard, to create opportunities for everybody, and to avert disasters. This book is dedicated to everyone working towards the good. I love that. All right. Computing is pop culture. Pop culture holds a disdain for history. Pop culture is all about identity and feeling like you're participating. It has nothing to do with cooperation, the past or the future. It's living in the present. I think the same is true for most people who write code for money. They have no idea where their culture came from. Alan Kay, an interview with Dr. Dobbs Journal. Or an interview with Dr. Dobbs, Journal 2012. It's a nice quote. All right, so table of contents. I don't think I'm going to go through all of this now, but let's just skim through it, right? So the book is broken down into 3 parts, and there's a summary of what those 3 parts are. The 3 parts being the foundation of data systems, followed by distributed data, and part 3, which is derived data. And he'll kind of provide a little bit of description of what that's about. But looking ahead, we're going to be tackling chapter 1 today, and probably not all of chapter 1. This will be a multi-part bit that I hopefully will get into before the week is through. The first section here being what is reliability, scalability, and maintainability. Again, I think these are some of the key themes for the author. It's in the subtitle of the book. And I think it is the overall roadmap for what this book is about. Um, and we can go into some of the sub headlines here, but I think for that we'll leave it. We'll dive into the chapter. Um, Progressing through part one, though, there we dive into data models and query languages, um, followed by storage and retrieval, encoding and evolution, and then that will be the end of the fundamentals. For distributed data, there's replication and partitioning and transactions. Um, the trouble with distributed systems, quite a bit of that. I think one thing I'm curious, and hopefully he'll get into, is observability. I think observability is really an underrated topic of distributed systems. It's certainly something we've been struggling quite a bit with. Uh, Consistency and consensus. And then, of course, we get into derived data. So I don't recall what derived data, what the overall theming of derived data is, but looking at it, we have batch processing, stream processing, and the future of data systems. So I think chapter 12 is going to be really, really interesting. Of course, it'll take a while before we get to page 489, but hey. All right. So the preface. If you've worked in software engineering in recent years, especially in the server side and back-end systems, you've probably been bombarded with a plethora of buzzwords related to storage and processing of data. NoSQL, big data, web scale, sharding, eventual consistency, ACID, cap theorem, cloud services, MapReduce, real time, and an exclamation point after every single word there. In the last decade, we have seen many interesting developments in databases, in distributed systems, and in ways we build applications on top of them. There are various driving forces for these developments. Internet companies such as Google, Yahoo, Amazon, and Facebook, and LinkedIn, Microsoft, and Twitter are handling huge volumes of data and traffic, forcing them to create new tools that enable them to efficiently handle such scale. Businesses need to be agile, test hypotheses cheaply, and respond quickly to new market insights by keeping development cycles short and data models flexible. Free and open source software has become very successful and is now preferred to commercial and bespoke in-house software in many environments. Finally, not finally, but next is CPU clock speeds are barely increasing, but multi-core processors are standard, and networks are getting faster. This means parallelism is only going to increase. If you work on a small team, you can now build systems that are distributed across many machines and even multiple geographical regions, thanks to infrastructure as a service, IaaS, such as Amazon Web Services, which, by the way, is not the only option. Quick sip of coffee, and playing a little bit of Eve Echoes in the background here, so I gotta update my mining. And then finally here, we have many services are now expected to be highly available. Extended downtime due to outages or maintenance is becoming increasingly unacceptable. So this is sort of setting the this is the world we live in now, right? So I think we have to accept these premises to be true, and I think largely they are. I think now, like having read these 6 bullet points, uh, let's see if we can break them down, right? So the first point was um, the big four plus are handling huge volumes of data and traffic, forcing them to create new tools that enable them to efficiently handle such scale. Now, you might be reading this and you might be, well, I'm not one of those companies, right? I don't work at a Facebook or an Amazon, etc. So does this apply to me? I think that it is fundamentally true, right? It's a whole discussion around what is uh, uh, big data. Like, how is data different today? And I think fundamentally, like, one easy cop out is, well, we have IoT now, right? You have IoT, and you're handling way more of those transactions. We have Um, um, I'm thinking SAP. What's the big CRM for SAP? Uh, we have CRM systems, we have analytics. We are gathering data faster than ever before. Storage has become cheap. That is one of the big reasons for that. And we're then taking that data and helping drive uh, um, business decisions. We're constantly optimizing. Now, is that good for society? It's debatable. And maybe this isn't the time and place to have that debate, but as the author stated, we strive to do good. Um, but I will share my personal opinion. I grew up watching commercials. I don't mind getting a commercial that is hand tailored to me. I'll be honest, my time spent on places like Instagram nowadays is mostly watching ads. I actually enjoy it. Now, I could be unique in that regard. Some people might be creeped out by it. There's plenty of media on the topic. Um, I'm much more concerned about governments. So that is my 2 cents there. Uh, but I think as software engineers, we need to accept that this is now the world we live in, and what used to be uh, what used to be a very simple problem with transit, where you had a database behind your back end with transactions and a little bit of cash in front, it might not fly. Every company is a technology company, and as if you're not a mom and pop shop, you'll probably get there, right? So the next point was businesses need to be agile, test the hypothesis cheaply, and respond quickly. Um, Now, this is a bit loaded, right? There is a really good book around building architectural foundations, which I'm not sure if this book will touch on, but you do need that foundation before you can actually exercise that level of flexibility with your data. It is easier said than done. Open source software has absolutely seen a rise. I think when this book was published, exceptionally so. The OpenStack is huge. It's extremely popular. Um, I can't claim to have come close to mastering it, but I've certainly been exposed to a lot of it. Working at a large enterprise, I still think that it is hasn't permeated the world as much as Silicon Valley likes to believe it has, right? But we'll see. Not being CPU bound, I think this is true in most cases. Um, and so even if you work in a small team, you're able to build distributed systems. This is true. This used to be a really, really hard problem. Leveraging um, infrastructure laid out by others is like Kubernetes is seriously simplifying this effort. Um, you can use Cloudflare and you can go, sit on the edge. You can go multi-region. I mean, it's amazing what you can do, but it's not cheap. So let's not don't jump headfirst into something like that. Yeah. All right. Let's move on. Move along. Let me unload my resources here. And I might speed up a little bit here in some of my reading, but so data intensive applications are, so let me see here. Do I want to take any notes on these topics, right? Um, so, so this is the preface, right? Um, I would say the thing that is most interesting to me, and I think I'll put an exclamation point here to indicate that in my notes. Um, how did we get here? Why are data intensive systems more prevalent today? this is storage is cheap. Rise of ML and analytics to drive CRM. And then what are some of the other ones? Building distributed systems is easier than before, even with small teams, right? Data-intensive applications are pushing the boundaries of what is possible by making use of these technological developments. We call an application data-intensive if data is its primary challenge. The quantity of data, the complexity of data, or the speed at which it is changing, as opposed to compute-intensive, where CPU cycles are the bottleneck. All right, I think that is worth noting. So I'll put that in quotes here. So this is an application is data in, can't type here, data intensive if data is its primary challenge. The quantity of data, the complexity of data, or the speed at which it is changing. Right. Let's do word route. Wow. There we go. That's better. As opposed to CPU intensive, where the CPU cycles are the bottleneck. So, hey, love. Oh, thank you.
What are you up to?
I'm recording.
Oh, you're sure.
Yeah. No, it's okay.
I'm excited about going to start Preface
Mm-hmm.
and like activities.
Mm-hmm. Me too.
And a friend of Michelle's pet family on the way back.
Oh, awesome.
There's like a bunch. So.
Awesome. I know it's not like super close to where it is, but
No, but as long as like we don't have to drive all the way home, we can still like sleep and drive.
yeah. All right. I'm gonna keep going. Bye. All right. All right. Where was I? So, yep. So here we are. We're not moving super slowly through this book. The tools and technologies that help data-intensive applications store and process data. Right. This is the thing I said that I will try to do, which is to move the book somewhere where you can actually see what I'm reading. All right. So this is where I'm at. The tools and technologies that help data-intensive applications store and process data have been rapidly adapting to these changes. New types of database systems, such as NoSQL, have been getting lots of attention, but message queues, caches, search indexes, frameworks for batch and stream processing, and related technologies are very important too. Many applications use some combination of these. The buzzwords that fill this space are a sign of enthusiasm for the new possibilities, which is a great thing. However, as software engineers and architects, we also need to have a technically accurate and precise understanding of the various technologies and their trade-offs if we want to build good applications. For that understanding, we have to dig deeper than the buzzwords. Fortunately, behind the rapid changes in technology, there are enduring principles that remain true, no matter which version of a particular tool you're using. If you understand these principles, you are in a position to see where each tool fits in, how to make good use of it, and how to avoid its pitfalls. That's where this book comes in. The goal of this book is to help you navigate the diverse and fast-changing landscape of technologies for processing and storing data. This book is not a tutorial for one particular tool, nor is it a textbook full of dry theory. Instead, we'll look at examples of successful data systems, technologies that form the foundation of many popular applications that have to meet scalability, performance, and reliability requirements in production every day. We will dig into the internals of those systems, tease apart their key algorithms, discuss their principles and their trade-offs they have to make. On this journey, we will try to find useful ways of thinking about data systems, not just how they work, but also why they work that way, and what questions we need to ask. After reading this book, you will be in a great position to decide which kind of tech. After reading this book, you will be in a great position to decide which kind of technology is appropriate for which purpose, and to understand how tools can be combined to form the foundation of a good application architecture. You won't be ready to build your own database storage engine from scratch, but fortunately, that is rarely necessary. You will, however, develop a good intuition for what your systems are doing under the hood, so that you can reason about their behavior and make good decisions, and track down any problem that may arise. Who should read this book? If you develop applications that have some kind of server backend storing or processing data, and your applications use the internet, i.e., or e.g., web applications, mobile apps, or internet-connected sensors, this book is for you. All right, moving the book back over. Boom, realign. This book is for software engineers and software architects and technical managers who love to code. It is especially relevant if you need to make decisions about the architecture of the system you work on. For example, if you need to choose tools for solving a given problem and figure out how to best apply them. But even if you have no choice over your tools, this book will help you better understand the strengths and weaknesses. You should have some experience building web-based applications or network services, and you should be familiar with relational databases and SQL. Any non-relational database and other data-related tools you know are a bonus, but not required. A general understanding of common network protocols like TCP and HTTP is helpful. Your choice of programming language or framework makes no difference for this book. If any of the following are true for you, you'll find this book valuable. You want to learn how to make data systems scalable, for example, to support web or mobile apps with millions of users. You need to make applications highly available, minimizing downtime and make them operationally robust. You're looking for ways to make systems easier to maintain in the long run, even as they grow and as requirements and technologies change. You have a natural curiosity for the way things work and want to know what goes inside major websites and online services. This book breaks down the internals of various databases and data processing systems, and it's great fun to explore the bright thinking that went into their design. Hi. There's a lot of words. 39%. Keep mining. We don't have any audience in chat. It's really disappointing, guys. Switch to non-mod settings. Alright, well, we're going to keep moving. So, sometimes when discussing scalable data, people make comments along the lines of, "You're not Google or Amazon, stop worrying about scale, and just use the relational database." There is truth in that sentiment. Building for scale that you don't need is wasted effort and may lock you into an inflexible design. In effect, it is a form of premature optimization. However, it's also important to choose the right tool for the job, and the different technologies each have their own strengths and weaknesses. As we shall see, relational databases are important, but not the final word on dealing with data. So, I'm going to write this down. I think that's worth, when we go through our book club here, to possibly reference that. So, um, you're not Google or Amazon. Stop worrying about scale and just use a relational database. We don't want to prematurely optimize. We do want to use the best tool for the job. Scope of this book. This book does not attempt to give you detailed instructions on how to install or use specific software packages or APIs. Since there's already plenty of documentation for these things, instead we discuss the various principles and trade-offs that are fundamental to data systems, and we explore the different design decisions taken by different products. In the ebook edition, we have included links to full-text online resources. All links were verified at the time of publication, but unfortunately links tend to break, frequently due to the nature of the web. If you come across a broken link, or if you're reading a print copy of this book, you can look up references using the search engine. For academic papers, you can search for the title in Google Scholar to find the open access PDF files. Alternatively, you can find the references at GitHub ept/DDIA-references, where we maintain an up-to-date links. I'm going to actually grab that link there and then share that in our Discord. So that is GitHub ept, right, DDIA references. Let's drop in there. Chapter 1 references. Alright. Okay. Let's keep moving. Keep moving. There we go. All right. So we look primarily at architecture of data systems and the way they are integrated into data-intensive applications. This book doesn't have the space to cover deployment, operations, security, management, and other areas. Those are complex and important topics, and we wouldn't do them justice by making them superficial side notes in this book. They deserve books of their own. Many of the technologies described in this book fall within the realm of big data buzzword. However, the term big data is so overused and underdefined that it is not useful in the serious engineering discussions. This book uses less ambiguous terms, such as single node versus distributed systems, or online interactive versus offline batch processing systems. This book has a bias towards free and open source software, FOSS, because reading, modifying, and executing source code is a great way to understand how something works in detail. Open platforms also reduce the risk of vendor lock-in. However, when appropriate, we also discuss proprietary software, closed source software, software as a service, or companies' in-house software that's only described in literature but not released publicly. So, the outline for this book. In part one, we discuss the fundamental ideas that underpin the design of data-intensive applications. We start in chapter one by discussing what we actually are trying to achieve, which is reliability, scalability, and maintainability, how we need to think about them, and how we can achieve them. In chapter two, we compare several different data models and query languages and see how they are appropriate to different situations. In chapter 3, we talk about storage engines, how databases arrange on disk so that we can find it again efficiently. And in chapter 4, we turn to data formats, aka data encoding and serialization, the evolution of schemas over time. In part 2, we move from data stored on one machine to data that is distributed across multiple machines. This is often necessary for scalability, but it brings with it a variety of unique challenges. We first discuss replication in Chapter 5, partitioning and sharding in Chapter 6, and transactions in Chapter 7. We then go into more detail on the problem with distributed systems in Chapter 8, and what it means to achieve consistency and consensus in a distributed system in Chapter 9. In Part 3, we discuss systems that derive some data sets from other data sets. Derived data often occurs in heterogeneous systems when there's no one database that can do everything well, applications that need to integrate several different databases, caches, indexes, and so on. In Chapter 10, we start with batch processing with that approach to derived data, and we build upon it with stream processing in Chapter 11. Finally, in Chapter 12, we put everything together and discuss approaches for building reliable, scalable, and maintainable applications in the future. So, again, I am super very excited for what this book is going to teach me. I have it is applicable to what I do every day, but more than that, it is exciting to kind of round out a lot of what I know now through this literature, and I think that's going to help me build something that I've been kind of working on, or thinking about, I guess, I think for the last 7 months, like pre-COVID. So, yeah, super excited. And beautiful introduction to this book. Mining away. All right, so references and further reading. Most of what we discuss in this book has already been said elsewhere in some form or another, in conference presentations, research papers, blog posts, code, bug trackers, and mailing lists in engineering folklore. This book summarizes the most important ideas from many different sources, and includes pointers to the original literature throughout the text. The references at the end of each chapter are a great resource if you want to explore an area in more depth, and most of them are freely available online. So I'm going to try to make time to dig into some of these. I think as I read chapter 1, I basically went through and highlighted every single reference I could find, which was probably not the best approach, but see if I can maybe pick 1 to 3 items and really like dig in, right? All right, so that was the preface, and yeah, we're not going to get through chapter 1, but let's keep going. So we are going to skip this. This is like book legalese, not interesting. All right. Here we are. Part 1, Foundations. Speaking of, I need to pick up the Foundation series. All right, Foundations. So this is kind of a we're restating what we just read again, but let's go through it. And I think, do we want to take notes on this? Yeah, let's. The first 4 chapters go through the fundamental ideas that apply to all data systems, whether running on a single machine or distributed across a cluster of machines. In Chapter 1, the introduction and we introduce terminology and approach that we're going to use throughout this book. It examines what we actually mean by the words reliability, scalability, and maintainability. How we can try to achieve those goals. Let me write that down. What? Not very consistent formatting here. Whoa. Alright. It's okay. Alright, so chapter 1 is terminology and the overall approach. Chapter 2 is compares data models and query languages. Chapter 3 dives into internals of storage engines. And chapter 4 is encoding and serialization. And how it and then evolves over time, right? Evolutionary architecture. All right. So, what is? I got to show you this picture. Look at this. Designing data-intensive applications. The big ideas behind reliable, scalable, maintainable. What is reliable? What is scalable? What is maintainable? We are building a map here. Reliable, scalable, maintainable applications. The internet was done so well that most people think of it as a natural resource, like the Pacific Ocean, rather than something that was man-made. When was the last time a technology with a scale like that was so error-free? Alan Kay, an interview with in the Dr. Dobbs journal. Many applications today are data-intensive as opposed to compute-intensive. Raw CPU power is rarely a limiting factor for these applications. Bigger problems are usually the amount of data, the complexity of the data, and the speed at which it is changing. A data-intensive application is typically built from a standard building blocks that provide commonly needed functionality. For example, many applications need to store data so that they or another application can find it again later. Remember that the result of the expensive operation to speed up reads, or allow users to search data by keyword or filter it by in various ways. Send a message to another process to be handled asynchronously, or periodically crunch a large amount of accumulated data via batch processing. So this is sort of the notes I've already taken here. Kind of do that so as we type, hopefully, things are always in view. It's getting warm in here. Probably shouldn't be chewing gum, but We're still so super quiet on the stream. Like, there's not a single question, guys. Um, you know, hopefully someone stumbles across this and finds this useful and interesting. And, again, if you want to join our Discord chat, join our book club, please. Like, I mean, building a community is a lot of fun. Um, and there's a lot of superficial ways to connect with people. I think meeting others around a common interest is I've made friends that way. So, all right, let me get back in there. So, let's review here, right? So, what constitutes an application? Well, um, databases, caches, search indices, stream processing, or batch processing, or both. So, if that sounds painfully obvious, that's just because these data systems are such successful abstractions. We use them all the time without thinking too much. When building an application, most engineers wouldn't dream of writing a new data storage from scratch because databases are perfectly good tools for that job. But reality is not that simple. There are many database systems with different characteristics. Because different applications have different requirements, there are various approaches to caching, several ways of building search indices, and so on. When building an application, we still need to figure out which tools, which approaches are the most appropriate for the task at hand. And it can be hard to combine tools when you need to do something that a single tool cannot do alone. This book is a journey through both the principles and the practicalities of data systems and how you can use them to build a data-intensive application. We will explore what different tools have in common, what distinguishes them, and how they can achieve their characteristic. In this chapter, we will start by exploring the fundamentals of what we're trying to achieve, which is, again, a reliable, a scalable, and a maintainable data system. We'll clarify what those things mean, outline some of the ways of thinking about them, and go over the basics. Um, go over the basics that we will need for later chapters. In the following chapters, we will continue to layer by layer, looking at different design decisions that need to be considered when working on a data-intensive application. Thinking about data systems. We typically think of databases, queues, caches, etc. as being very different categories of tools. Although a database and a message queue have some superficial similarities, both store data for some time, they have very different access patterns, which means different performance characteristics and thus very different implementation. So why should we lump them all together under the umbrella term like data systems? Many new tools for data storage and processing have emerged in recent years. They are optimized for a variety of different use cases, and they can no longer neatly fit into the traditional category. For example, there are data stores that are also used as message queues, such as Redis. There are message queues with database-like durability guarantees, like Apache Kafka, and the boundaries between the categories are becoming blurred. So I find that very interesting. Let me get into why. So, in one breath, the author is saying, look, we can no longer neatly fit all of these problems into a single solution. And yet, where the author ends is by saying the lines are getting blurred, right? So, honestly, I think of things like Postgres. Postgres is of course, thought of as a top-notch SQL database. Yet the amount of NoSQL expanded functionality that it has, and by no means is it exclusive. Both Oracle and Microsoft's MS SQL, Microsoft SQL database is in that same category, but of course they're expensive. So Postgres is the example. You can build a key value store document storage within it. What I don't know, unfortunately, is what the underlying data storage model for it is, and whether it would perform as well as, say, Mongo in that regard. But the capabilities are often there. When you think of Postgres, you're like, well, Postgres doesn't shard well. That's just right. Like, shouldn't I be using Cassandra? Maybe, but again, there are implementations of it. Now, of course, the one that comes to mind is the commercial variety, which is Greenplum, but it's possible, right? It's possible because under the hood, everything is design pattern and algorithm and implementation, and it is possible to build these sort of multi-purpose data stores. They exist. The other one that really comes to mind for me, and of course I don't really know what the under the hood implementation is exactly like. They could actually just be switching databases for you, but it would be something like it's the offering on Azure. It's not DynamoDB, but it's sort of in that similar category. Gosh, I wish I could remember what it is. But you could quite literally move a slider to determine what level of consistency you're looking for, right? So it is an interesting point to take. I think now I think that the takeaway here, for me at least, isn't to go and well, shoot, if this is where we're headed, why not skip all of this altogether? We're just going to stick to this one database and just buy our way up. It's certainly a solution, but as software engineers, I genuinely believe that an understanding of basic principles is so very important. It's why we cannot dismiss things like Kubernetes, right? John and her group will call them out by name here. Believes it's something that will come and go. That may be true, but I mean, it's almost like saying, look, I write software applications and I don't need to understand the hardware under which it runs. You don't have to be an electrical engineer, but like having an understanding of why RAM is faster than reading from disk has value, and it helps you drive your decisions in the long run. And I know it's a very simple example, but understanding why one database is more applicable than the other by looking at them through this sort of very narrow lens is going to help you make that decision when it becomes a slider. I hope that makes sense. All right. I should probably make a note of that, actually. I think that's worth a discussion point. So, why understand different data systems if they're all converging? Basic principles help drive decisions when it's a slider. All right, that's a type of note that will only make sense to me, but um, hopefully it'll be enough to trigger my memory when we have that discussion with the group. So, all right. Where are we? Not very far. All right. So categories are becoming blurred. Secondly, increasing many applications now have such demanding or wide-ranging requirements that a single tool can no longer meet all of the data processing and storage needs. Instead, the work is broken down into tasks that can be performed efficiently on a single tool, and those different tools are stitched together using application code. For example, if you have an application managed caching layer using Memcache or similar, or a full text search server such as Elasticache or Solar, separate from your main database, it is normally the application's code responsibility to keep those caches and indices in sync with the main database. Figure 1.1 gives a glimpse of what this may look like. We will go into detail in later chapters. So, let me, you know what? Let me highlight this, or at least make a note of this. So, what the author is saying here is, um, it is the application's responsibility to keep the various, um, to keep the wide-ranging, uh, various application responsibility to keep the various where did I read that? All right, keep the various data systems in sync. Um, Caching, full text search, main database, messaging queues. All right. Move that up. And of course, that's an example of what that may look like. So, when you combine several tools in order to provide a service, the services interface or the application programming interface or the API for it usually hides those implementation details from the clients. Now you have essentially created a new special purpose data system from smaller general purpose components. Your composite data system may provide a certain guarantee, i.e., the cache will be correctly invalidated or updated on writes, so that outside clients see consistent results. You're now not only an application developer, but also a data systems engineer. So, when your application is responsible for keeping the cache in sync or stitching these smaller components, you are now not only an app developer, but a data systems designer. Congratulations. It's a free promotion. All right. If you're designing data systems or a service, a lot of tricky questions arise. How do you ensure that the data remains correct and complete, even when things do go wrong internally? How do you provide consistently good performance to clients even when parts of your system are degraded. How do you scale to handle an increase in load? What does a good API for a service look like? There are many factors that may influence the design of data systems, including skills and experience of the people involved, legacy system dependencies, the time to scale for delivery, your organization's tolerance for different kinds of risks, regulatory constraints, etc. These factors depend very much on the situation. I do apologize, this is an incredibly slow process, but I'm taking these notes for myself in order to construct a good overall summary for the group later. So I do want to jot these things down, right? So what constitutes good data system design, right? And these are questions like responding to errors, sure. Good performance when the system is in degraded state. So basically operate when some things break. Scale to handle increased load. Good API design. What about the next bit, right? So constraints. We might have skills and experience of the people involved. We have legacy system dependencies, the time scale for delivery, and organizational tolerance for risk. Cannot say that word. Regulatory constraints. And so. In this book, we focus on three concerns that are important in most software systems: reliability, scalability, maintainability. I'm not sure how many times I've said those words. So what is reliability? Definitions. All right. Reliability. The system should continue to work correctly, performing the correct function at the desired level of performance. Desired level of performance. I think that's an important thing to emphasize here. Performs the correct function at the desired level of performance. Scalability. The system grows in data volume, traffic volume, and complexity. Grows in data volume, traffic, complexity. And there are reasonable ways to handle this growth. Maintainability. Be able to continue to work on the system in a productive way. Good enough. All right. These words are often cast around without a clear understanding of what they mean. In the interest of thoughtful engineering, we will spend the rest of this chapter exploring ways of thinking about reliability, scalability, and maintainability. Then, in the following chapters, we will look at the various techniques, architectures, and algorithms that are used in order to achieve those goals. So, reliability is first. All right, reliability. Um, Everybody has an intuitive idea of what it means for something to be reliable or unreliable. For software, typical expectations include the application performs the function that the user expected. It can tolerate the user making mistakes. It performs, its performance is good enough for the required use case under expected load and data volume. The system prevents any unauthorized access or abuse. If all those things together mean working correctly, then we can understand reliability as meaning roughly continue to work correctly even when things go wrong. The things that can go wrong are called faults. The system that anticipates faults and can cope with them are called fault tolerant or resilient. Why is that? Oh, dyslexia. Um, the former term is slightly misleading. It suggests that we can make a system tolerant of every possible kind of fault, which in reality is not feasible. If the entire planet Earth and all the servers on it were swallowed by a black hole, tolerance of that fault would require a web hosting in space. Good luck getting that budget item improved. So it only makes sense to talk about tolerating certain types of faults. Now I'm putting quote marks here. Obviously, that's not what the author said, but I wanted to capture just a general idea. And for me, the quotes are just a way to say that this is something I've read in the book. I'm not writing pure citations. By the way, just if it isn't clear, I do highly recommend anybody goes out that is interested in this material actually buys the book. Um, you know, I'm doing this as something that, well, we'll leave it as it is, right? I think if at any point I would get a cease and desist, I would do so, but I do hope that this actually helps drive the author's sales. The book is fantastic. All right. All right. Let's keep going. Switching over. Note that the fault is not the same as a failure. A fault is usually defined as a component of the system, deviating from its spec, whereas a failure is when the system as a whole stops providing the required services to the user. It is impossible to reduce the probability of fault to zero. Therefore, it is usually best to design a fault tolerance mechanism that prevents faults from causing failures. In this book, we cover several techniques for building reliable systems from unreliable parts. I'm kind of repeating myself here, but all right. Counterintuitively, in such fault-tolerant systems, it can make sense to increase the rate of faults by triggering them deliberately. For example, by randomly killing individual processes without warning. Many critical bugs are actually due to poor error handling. By deliberately including faults, you ensure that the fault tolerance machinery is continually exercised and tested, which can increase your confidence that faults will be handled correctly when they occur naturally. Um, I'm not going to get into what Netflix cast monkeys are. Um, Obviously, if there were some folks on chat that are interested, I'd be happy to talk about it. Um, yeah, but for the time being, I'll leave that up to you to explore. Um, but there's a bunch of really awesome ones. Um, Although we generally prefer tolerating faults over preventing faults, there are cases where prevention is a better cure, because no cure simply exists. This is the case with security matters. For example, if an attacker has compromised a system and gained access to sensitive data, that event cannot be undone. However, this book mostly deals with the kinds of faults that can be cured, as described um, in the following sections. Some faults are some faults do not have a cure, such as security breaches. Failure might be the only word. Hardware faults. When we think, all right, so that kind of covered that section there on reliability, right? So this is now, I don't know how to demarc sections for myself. I'm going to do this. I'm just making up things as I go along. Hardware faults. When we think of causes of system failure, hardware faults quickly come to mind. Hard disk crashes, RAM becomes faulty, the power grid has a blackout, someone unplugs the wrong network cable. Anyone who has worked with large data centers can tell you that these things happen all the time when you have a lot of machines. Hard disks are reported as having a mean time failure of about 10 to 50 years. Thus, on storage cluster with 10,000 disks, we should expect an average of one disk to die per day. Um, Hard disks are reported as having a mean time to failure of about 10 to 50 years. Thus, on a storage cluster with 10,000 disks, we should expect, on average, one disk to die per day. I love that. I'm going to try to memorize that and use that to sound smart. Our first response is usually to add redundancy. Um, all right. To the individual hardware components in order to reduce the failure rate of the system. Disks may be set up in RAID configurations, servers may have dual power supplies and hot swappable CPUs, and data centers may have batteries and diesel generators for backup power. When one component dies, the redundant component can take its place while the broken component is replaced. This approach cannot completely prevent hardware problems from causing failures, but it is well understood and can often keep the machine running uninterrupted for years. Until recently, redundancy of hardware components was sufficient for most applications, since it makes total failure of one single machine fairly rare. As long as you can restore a backup onto a new machine fairly quickly, the downtime in case of failure is not catastrophic in most applications. Thus, multi-machine redundancy was only required by a small number of applications for which high availability was absolutely essential. However, as data volumes and application computing demands have increased, more applications have begun using larger numbers of machines, which proportionally increase the rate of hardware faults. Moreover, in some cloud platforms such as AWS, it is fairly common for virtual machine instances to become unavailable without warning. As the platforms are designed to prioritize flexibility and elasticity over a single machine reliability. Hence, there is a move towards systems that can tolerate the loss of entire machines by using software fault tolerance. Techniques and preferences in software fault tolerance techniques in preference or in addition to hardware redundancy. Such systems also have to have operational advantages. A single server system requires planned downtime if you need to reboot the machine, to apply the operating system security patches, for example, whereas a system that can tolerate machine failure can be patched one node at a time without downtime for the entire system. This is also known as rolling upgrades. Due to the requirement for more machines, the trend has shifted to software fault tolerance over hardware redundancy. This also comes with when done correctly, this comes with the advantage of being able to do rolling upgrades. All right. How are we doing on time here? It is getting pretty late. Might call it a day here and pick this up tomorrow. Although I think I do want to make my way over to scalability. So I'm going to pick up the speed here. I'm just going to power through the text, take the notes where appropriate, and maybe not do as much talking. But yeah. Software errors. We usually think of hardware faults as being random and independent from each other. One machine's disk failing does not imply another machine's disk is going to fail. There may be weak correlations, for example, due to a common cause, such as the temperature in the server rack, but otherwise it is unlikely that a large number of hardware components will fail at the same time. Another class of faults is a systemic error within the system. Such faults are harder to anticipate, and because they are correlated across nodes, they tend to cause many more system failures than the uncorrelated hardware faults. Examples of this include a software bug that causes every instance of the application server to crash when given a particular bad input. For example, consider the leap second of June 30th, 2012, that caused many applications to hang simultaneously due to a bug in the Linux kernel. Another example might be a runaway process that uses up some shared resource, CPU, time, memory, disk space, or network bandwidth. A service that the system depends on that slows down becomes unresponsive and starts returning corrupted responses. A cascading failure where a small fault in one component triggers a fault in another component. So, software. Um, these can be harder to anticipate and result in systemic errors. Examples. The bugs that cause these kinds of software faults often lie dormant for a long time until they're triggered by an unusual set of circumstances. In no circumstances it is revealed when the software is making some kind of assumption, and in the environment, while that assumption is usually true, it eventually stops being true for some reason. Retry bug. There's no quick solution to this problem with systemic faults in software. Lots of small things can happen. Carefully thinking about assumptions and interactions in the system, thorough testing, process isolation, allowing processes to crash and restart, measuring, monitoring, and analyzing system behavior in production. So, solutions. None are perfect, but careful thinking about assumptions and interactions. Thorough testing. Process isolation. Allowing for processes to crash and heal. Measuring, monitoring, and analyzing behavior in production. All right. Human error. Humans design and build software systems, and the operators who keep systems running are also human. Even when they have the best intentions, humans are known to be unreliable. For example, one study of large internet services found that configuration errors by operators were the leading cause of outages, whereas hardware faults, server errors, and networks played a role in only 10 to 25% of the outages. That is incredible. One study of large internet services found that configuration errors by operators were the leading cause of outages, whereas hardware faults played a role in only 10 to 25% of outages. And I'm going to actually make a note here of that study. How do we make our systems reliable in spite of unreliable humans? The best systems combine several approaches. Design systems in a way that minimizes the opportunity for error. For example, well-designed abstractions, APIs, admin interfaces make it easy to do the right thing and discourage the wrong thing. However, if the interfaces are too restrictive, the people will work around them, negating the benefits. So this is a tricky balance to get right. Solutions. Design systems that minimize for opportunities for human error. This means well-designed abstractions, APIs, admin interfaces. If done poorly, people will work around them and negate the previous effort. All right. Decouple the places where people make the most mistakes. Solutions. Decouple the places where people make the most mistakes from the places where they can cause failure. Sandbox environment. With real data that doesn't impact real users. Test thoroughly at all levels, from unit tests to whole system integration tests and manual tests. So we had a long conversation about this a few days ago at work. Something I think I might do just a stream on later on as well. Like, what are the different types of tests? What is an integration test compared to an end-to-end test? When should you apply which? The devil's in the details there. Oh, look at that. Another mining run complete. Dock it up. And I'm going to stop here. So, allow quick and... let me scoot over. Allow quick and easy recovery from human errors to minimize the impact that causes failure. For example, fast rollback configurations. Set up detailed and clear monitoring for performance metrics, and error rates. This is sometimes called telemetry, and alright, I'm gonna make a note. I think I do want to read that one. 14. I think this is one of the hardest things, honestly. Observability is just really, 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 really hard. I mean, okay, like, we can get into what hard means, right? Is it harder than debugging assembly? Debatable. What I'm saying is it is hard. It is often underestimated, and is one of those softer things that is, therefore it's hard. It's like, the way to think about what I'm trying to say here when I say it's hard, it's like, imagine there's a dartboard and the bullseye is you getting observability perfectly, right? It is really hard to, like, you might get close, but hitting that bullseye is very difficult, as opposed to, debugging even a hard problem. Like, eventually you get there, right? You're walking down the path towards a solution. With observability, you're just always like, oh, is this good enough? Did I've properly uncover all the unknown unknowns? So that's why it's hard. Implementing good management practices and training, a complex and important aspect and beyond the scope of this book, right? So, good management and training practices. I do think that we try to do this well at work. Like, the team that I lead, like, we try. Yeah. I would love it if all the things that are outside of the scope of this book had some reference of, like, go read this book. I think sometimes these topics are just simply not covered in depth. All right, so how important is reliability? Reliability is not just for nuclear power stations and air traffic control software. More mundane applications are also expected to work reliably. Bugs in business applications cause lots of productivity and legal risks. If figures are reported incorrectly. And outages of e-commerce sites can have huge costs in terms of lost revenue and damaged reputation. Even in non-critical applications, we have the responsibility to our users. Consider a parent who stores all of their pictures and videos of their children in your photo application. How would they feel if that database suddenly got corrupted, etc., etc., etc.? Reliability is very important. I'm getting very tired. I hope this was interesting, entertaining. I don't know if I'm going to just, post this video as is unedited. I'm probably going to do that because I just don't have time to go through and do, like, proper editing. I know there were a bunch of lulls in this. I don't know how exciting or interesting it is to listen to me read. But, again, I really hope that you would consider joining our community, Software Over Coffee. Um, Discord is where it's at. And yeah, just say hello sometimes. Have a good night.